Pythagoras was born on the island of Samos in Greece and did much traveling throughout Egypt, learning, among other things, mathematics. Not much more is known of his early years. Pythagoras gained his famous status by founding a group, the Brotherhood of Pythagoreans, which was devoted to the study of mathematics. The group was almost cult-like in that it had symbols, rituals, and prayers. In addition, Pythagoras believed that numbers rule the universe, and the Pythagoreans gave numerical values to many objects and ideas. These numerical values, in turn, were endowed with mystical and spiritual qualities. Legend has it that upon completion of his famous theorem, Pythagoras sacrificed 100 oxen. Although he is credited with the discovery of the famous theorem, it's not possible to tell if Pythagoras is the actual author. The Pythagoreans wrote many geometric proofs, but it is difficult to ascertain who proved what, as the group wanted to keep their findings secret. Unfortunately, this vow of secrecy prevented an important mathematical idea from being made public. The Pythagoreans had discovered irrational numbers. If we take an isosceles right triangle with legs of measure 1, the hypotenuse will measure square root 2. But this number cannot be expressed as a length that can be measured with a ruler divided into fractional parts, and that deeply disturbed the Pythagoreans, who believed that all is number. They called these numbers allegon, which means unutterable. So shocked were the Pythagoreans by these numbers, they put to death a member who dared to mention their existence to the public. It would be 200 years later that the Greek mathematician Eudoxus developed a way to deal with these unutterable numbers. And now we're going to go ahead and talk about this theorem of Pythagoras. Okay, so first thing I'm going to do is start by creating a right triangle. How do I know that this is a right triangle? I am going to take these points and measure the angle. I see that I have a 90-degree angle. Good, I have a right triangle. This is in the way, so I am going to hide these labels for a second. Okay, so back to my right triangle. What I need to do is measure the hypotenuse, but I can't just look at it and figure it out. Sure, I could use Sketchpad to measure, and I am kind of lazy, but you know what? I'm going to do something else. What I'm going to do is use a formula to find the third side of a right triangle. You'll notice as I move things up and down over here, the numbers are changing. Let's just go with that. Okay. So, first thing I'm going to do is make a square based off of the sides of the triangle. I'm going to start by taking the square, over here, and making a square there. There's a square of the hypotenuse. I'm also going to do that with leg A and leg B. Next thing I'm going to do is go ahead and make some measurements of these squares. Hey, congratulations, Mr. Chavez, you've made squares. What about them? All right, so first thing I'm going to do is measure the area of this square, and we'll see that this square is 3.9 square inches, give or take. Then I'm going to measure this square, and I'll notice that I get 3.0 square inches. Then what I'm going to do is measure this. So these are the squares based off of the legs of a right triangle. Now I'm going to make a square. I'm going to measure the square based on the hypotenuse of that right triangle. And what we notice is that if I take the area of the first square and I add it to the area of the second square, I get the area of the third square. Now here's the really cool part, because no matter how I change them up, I always end up with the area of the two smaller squares adding up to the area of the larger square. Well, what does that really mean? Well, what we're going to do in a minute is talk about how this relationship helps us calculate the missing third side of a right triangle. So based on that explanation, we have the square of the leg. So if we were to take a square from the leg, and the square of the other leg, and that would equal the square of the third leg, or the hypotenuse. We're going to extend all the way up over here. It's going to be a square. Trust me, it's just going off the screen somewhere. So really what that means is that if we take the area of this and the area of this, it will add up to the area of this. Another way it's represented, instead of just leg squared plus leg squared equals hypotenuse squared, is a squared plus b squared equals c squared. So given the two sides of a right triangle, you should be able to find the third. Let's take a look at a couple of examples. And feel free to work on these examples while I'm explaining. So first off, we have a right triangle. On triangle ABC, angle C equals 90 degrees. AC equals 4 centimeters and BC equals 3 centimeters. This is important information. So the most important part, though, is that angle C equals 90 degrees, because we can't use the Pythagorean theorem if we don't have a right triangle. So in this case, I have a squared plus b squared equals c squared. And c squared, if we remember back to the last screen, is going to be my hypotenuse. So what I'm going to do is substitute 3 for a, so I'm going to have 3 squared plus 4 squared, because I'm substituting 4 for b, and that's going to get me my answer of c squared, not c. That's important. So 3 squared plus 4 squared is 9 plus 16 equals c squared. 25 equals c squared. But my answer isn't 25, remember, because I have c squared. What I need to do in order to undo that square value is take the square root. So what I'm going to do is take the square root of 25. And the square root of 25 is 5. So then my c value equals 5. Which means then the length of AB, which is what I'm looking for, is 5 centimeters. Let's take a look at the next example. In triangle PQR, angle P equals 90 degrees. And if you don't recognize that, the little square at the bottom of the triangle, that lets you know that it is a right triangle. So even if it doesn't tell you that it's 90 degrees, if you see the little square, that lets you know that it is 90 degrees. But anyway, back to the problem. So PQ equals 24 centimeters, and QR equals 25 centimeters. We need to find the length of PR. Here's where some people can make mistakes. Because we have a squared plus b squared equals c squared, some people think that the unknown is always going to be c squared. That's not true. C squared always references the hypotenuse. But in this example, the hypotenuse is already given. So we're going to have to reorder things a little bit. And I know that if I take a squared plus b squared, I'm going to get c squared, but I'm already given c squared, and that is 25. So I'm going to have 25 squared, and then I don't know what, and it doesn't matter which one we choose. We could choose either a squared or b squared. Let's say that b squared is 24. So then we're trying to find out a squared, which means in order to find out a squared, what I'm going to have to do is subtract 24 squared from both sides. All right, order of operations, hold on here. A squared, so a squared equals 25 squared minus 24 squared. Now, you might think that you could just subtract 25 from 24 and leave you with 1 and then square that to get 1. That's not true. Remember the order of operations. You need to multiply before you can subtract. So we have 25 squared minus 24 squared. I'm going to take a little shortcut and let you know that they're very large numbers, but you do end up with a squared equaling 49. So now we know that a squared equals 49. We can take the square root of both sides because I just want a. And then so that leaves me with a equaling 7. So then that means the length of PR is 7 centimeters. All right, here we go.